Okay, good afternoon and welcome to session 8 of the Sunoikisis Digital Classics Spring Semester 2018. This session is the first of 2 sessions on introducing Python, the programming language, and this session, which will be run by Simona Stoyanova from the Institute of Classical Studies in London and Francesco Mambrini from the German Archaeological Institute in Berlin, will be the introduction to Python and regular expressions, and we'll talk a little bit about issues of information extraction and named entity recognition at a basic level. I believe Simona is going first, so I'll hand over to her.
Hello, thank you, Gabby. Let me share my screen. Okay.
Great.
So, as Gabby said, this is a session on Introduction to Python and basic named entity extraction. And in this session, you will not be able to follow along and coding at the same time as Francesco and I are, but here on the Jupyter notebooks, we have shared our training materials, which we will be using during this session. So you can download them now and follow along, or download them later after you've seen the video. To use them, you would need to install Jupyter Notebook, which is a piece of software. And we've provided a link to this installation page on the class outline page. And you can just follow these instructions and set it all up. Okay, so the first half of this session will introduce the basics of the Python programming language, and there's a handy table of contents at the very beginning. Once you've seen the session and want to, for example, remind yourselves of a particular bit of the class. So Python was created at the beginning of the 1990s and is still under development. It's been developed by a non-commercial foundation, and Python is used for all sorts of things in all kinds of areas of both research and business, including NASA and Google and digital humanities, as it happens. You might want to pay attention to the fact that there are 2 versions of Python, Python 2 and Python 3. We will be working today in Python 3, which has much better Unicode support. And since we'll be working with texts, that's a very important feature for us. But do bear in mind that if you look at codes, pieces of code, from a couple of years ago or more, they might be in Python 2. There are slight differences, so just so you know that it's good practice to check which version of Python any given piece of code is written into. So, shall I zoom in a bit? Is this visible?
Zooming in a little bit would be nice, yes, thanks.
Is this better?
That's much better, thank you.
Okay, thank you. So the basic syntax of Python, anything that is prefixed with the hash, we call a comment. This is a piece of text that you can put in as a reminder to yourself, as an explanation, as something that's not code to be executed. So anything you want to say, which is not piece of code you expect the computer to do something with, you put in a comment like this. And then we have 2 plus 3, which is now something that we want to calculate. And oops, if we run it, so this button here, the play button, means run the cell, which means execute the code in the cell I'm currently in. And we want to calculate 2 plus 3, and the result is 5. Then, so this was an example with numerical calculations. Python also works with text, as we already said. So we want, for example, to print a phrase, and we use the print function, and inside the parentheses we put the text we want printed. We run, and the result is our text. So as you saw, we might want to execute certain types of operations, and we might want to execute them more than once. We might want to print results, we might want to process the results for some purpose or other. So the basic thing that you can do in Python is store something, a process, in a variable. So variable is something like a treasure chest, like a box, where you put something that you want to use later on, something you want to use more than once, and something you want to refer to at a later stage. So in this case, we have a variable named result, and the content of the variable, the value of the variable, is our calculation 2 plus 3. We want to see what the variable is, then we print it, and we get the result, which is number 5. So result is the name of the variable. The variable itself is what lies after the equal sign. And we use the name to refer to the variable and to use it at a later stage. So what will happen if we want to execute the following code? Result, that's our variable from the previous cell over here, plus 5. We run it and we get 10, because result, as we saw up there, is the sum of 2 plus 3. So this is how you use a variable at some point later in your code to do something else. So what types of values can we put into variables? We can put integers, we can put strings of text with or without white space in them and punctuation and all sorts of things. We can put floats or booleans. If we're not sure, and it's important that we do know what type of variable we have when we work with them, if you're not sure what your variable is, you can always check with the type function and put the variable in the parentheses of the type function. Execute the code. So this sentence, we are told this variable is a string, which is correct. The next example is a float. The next example is a string. So result is a variable, but the variable contains a string. As you've seen already, we declare strings with either single or double quotes. It doesn't make a difference which one, as long as you are consistent. So if in hello, in the variable hello, my content is the text goodbye, if I put one double quotation mark and one single quotation mark, that raises an error. And if I bring back the double quotation mark, now this is correct. So as long as you use the same quotation marks every time, it should be fine. It's your choice whether or not they're single or double. Right, so in cell 9, we have the variable hello with the content goodbye. We print the variable and we get the text goodbye. In the next cell, we have the same. So we have already run a cell which contains the variable. So the next time we want to use it, we don't need to repeat it once we've already executed it in a previous cell. Okay, and in the last example, we have a different type, which is a string as well. But if we remove the quotation marks, now we have a type integer. So every time you surround your variable with quotation marks, that would mean that it's a string. If you want to treat the 2 as a number 2, then remove the quotation marks. Why do we care what type our variables are? So, for example, in this cell, we have 2 plus 3, but they're in quotation marks. So if we try to execute this operation, we get a concatenation. So we stick together the 2 strings, 2 and 3. We don't get a sum of the numbers 2 and 3. What we actually wanted to do is to calculate the sum of 2 and 3. There are 2 ways to do this. In the first, on line 2, the first option, we can use the int function to turn a string into an integer. And if we execute this, we have 5, which is what we wanted to get. Right, I'll comment this and move on to the second possibility. Or we can simply delete the quotation marks so that the 2 or 3 are now not strings, but numbers. We execute again, we get the same result. So when we work with strings, so things that have quotation marks, the plus sign means concatenation, so putting them one next to the other. When we work with integers, the plus means a plus sign, so it sums them. A further example, so we want to put the pieces of this sentence back together using these variables. The sentence has to say, when Caesar says do this, it is performed. Now, since this session is being recorded on the 15th of March, I thought it was appropriate to use some examples from Shakespeare's play Julius Caesar. So there will be a few of these in this presentation. So in variable A, we have the text do this. In variable B, we have the text it is performed. And then we want to print the whole phrase, starting with when Caesar says, then add the content of variable A, plus then add the content of variable B, which is concatenation, as we already said. And the result is the line, when Caesar says do this, it is performed. Now, more exciting things we can do with strings, apart from just sticking them together, we call basic string manipulation, and this is achieved by a number of string functions, which Python has. Now, just to let you know that these string functions, if you follow the link, they lead to the official Python documentation if you want to read a bit more than we've provided in the Jupyter Notebook. So all of these are links. So the string function upper turns a piece of text all into uppercase, like this. Notice that here I'm using the single quotation marks. Again, doesn't make a difference as long as I'm consistent. The opposite, the function lower, turns text into lowercase. The function rstrip strips all white space on the right side, so at the end of a string, and lstrip would get rid of any white space on the left-hand side, so at the beginning of the string. So in this case, I have a sentence that includes a large piece of white space, and I want to get rid of it. So I perform the strip function on it, like this. Then
You've got a full stop in the way, that's why that didn't work, isn't it?
Sorry, what? Oh, it didn't work. Yes, thank you. I didn't. Yes, of course. There you go. Thank you, Gabby. Yeah, so that was white space with a full stop, which obviously wouldn't count because the full stop is not white space. And now it is only white space, so it works, yes. Right. The next function is capitalization. I'm going to show you just a few of these. Again, if you want to explore more complicated string manipulation functions, follow the links to the documentation and you'll see a full list of this, but this is just a taster of what we can do with strings in Python. Right, so count returns a number of the occurrences of a string. So we have a variable sentence with the fault the abruptus is not in our stars but in ourselves, that we are underlings, and in this sentence, in this variable, we want to count the number of times we have the occurrence of an S followed by a white space. We execute and we have two occurrences, and those would be is not and ourselves that. We can also, more interestingly, replace parts of text with something else. And the way the syntax works is we put the old, so the original word, the original piece of text first, and then following a comma, we put the new text we want to replace it with. So in the variable S, we have the lines, people and senators be not affrighted, fly not, stand still, ambition's debt is paid. We want to replace in the first line the word affrighted, which is sort of antiquated Shakespearean weird English, with the modern word afraid. So we execute the replace function, and in the first place within the parentheses, we put the original word. After a comma, we put the word we want to replace it with. We execute and we have a new line, people and senators be not afraid, etc. We can also split strings and have a list of words or a list of clauses depending on how we separate them. So by default, the split function splits by white space. So in these two lines, if we execute print s split, we get a list of words separated by a comma. But these words in the original text are all separated by white space. If we want, however, to split those two lines by the semicolon, for example, then in the parentheses of the function split, we put the punctuation marker according to which we want to separate our string. Now we execute and we get the two clauses of this sentence. If we can split something, we can join it back again as well. So, slightly longer sentence with several semicolons in this variable. First, right, let me comment out the joining because we will do the splitting first. First, we split the string by the comma and we print, and we see that the line is split according to wherever we have a comma in the text. Now we want to join it back again, but this time instead of the comma, we want to join the string by a hyphen. We execute, and then we have the second part of the result over here, where we can see that every time we had a comma in the original text, now we have a hyphen. We can also turn a piece of text into a title by capitalizing every word, like this. And something that's going to come up and be useful when we get to Francesco's part of the session is calculating the length of a sequence, of a string, which can happen in two ways. So in the first example, we use the two functions print and length together. So print me the length of the phrase, how long am I? There's another way of doing it, and that's declaring a variable with some content and then printing the length of the variable. Those two things do the same thing in the end. And we get the result from the first example and the result from the second example. Right, that was simple string manipulation. For more complex and more interesting things to do with strings, we're now going to talk briefly about regular expressions. But before we can do that, we need to talk about importing modules. So modules are bundles of Python code that perform specific functions that probably not everybody wants to use. So they're not included into the general Python code that you'll get when you install Python on your computers. So if you want to use a specific model with specific functions, you need first to import it. And the code for this is simply the word import and the name of the module. And you'll see in a minute how this is done. And regular expressions is a separate module in Python which we need to import before we can use it. So what are regular expressions? A regular expression is a special text string which you use to describe a search pattern that you want to look for in your text. And this search pattern allows you to match anything that fits the requirements of this pattern. So for example, the expression capital A to small z would mean all the letters from A to Z, both capitalized and not, and so on. And we will see a few examples of this. The syntax of regular expressions is as follows. So we have a variable which I've called result for this example, and then we perform the function search, so search regular expression, the following pattern, the following pattern in the following text. So for example, find me the pattern ABC in the text string ABCDEFG, etc. So here I've listed a couple of basic matches just for you to read. We're going to see all of them in action, but this is a bit of sort of further information to look at later on. So first of all, we import the regular expressions like this. If you want to read a bit more about them, you can read their help, which explains what they are, links to the documentation, and gives you some special characters, etc. This is all stuff that we're going to briefly look at, but this is further documentation. So the first match that we're going to try to do, in the text, they were the Ides of March. We want to find, so we declare a variable found. We want to find if the letter A appears anywhere in the text. So we have a variable find, then we perform the search regular expressions, the pattern A in the variable text, and then we print, and we do have indeed the character A appearing in this text. Now, if we want to find more than one occurrence of our search pattern, we don't use search, we would use find all. So in the second example, we have a text, then we want to find all occurrences of the character A in our text. Then we print the result, and we have 4 times the character A. Let's look at a more interesting pattern now. We have a different text in our text variable now, and we want to find not just a single character, but an H followed by 4 characters of any type. So full stop means any character. That's a special, it has a special meaning in regular expressions, the full stop. It doesn't mean a full stop, it means any character. So find me H followed by 4 characters followed by an E. And we have our result, which includes, as you will see, white space. That's counted as a character. So regular expressions use a number of modifiers to allow us more robust searching. For example, the asterisk means match 0 or more repetitions of the expression. A plus means 1 or more repetitions of the expression, and so on and so forth. You can have a look at those and experiment with them when you go over the notebook and see what different results you get when you use them and how to use them, as it's explained here. So let's use the question mark now, which means 0 or 1, so an optional pattern. So in text, we have again a piece of text for us to look for things in, and in the find all, we want to find any character followed by UCH, optional. We run it and we find much and such. So for example, if you wanted to see how many words in a certain piece of text end with UCH, if that's something interesting for you, using regular expressions would be the most robust way of doing that. Now, as we mentioned, the full stop and the question mark have special meaning. And if we want to actually match a full stop or a question mark as part of our search pattern, we would need to escape them so that they no longer mean a special character, but they mean punctuation markers. We do that, the escaping of special characters, with the backslash. And here is a list of special characters and escaping special characters for you to have a look at later on. And to see what they mean. For example, \W mean any alphanumeric character, so any letter or a number, and so on and so forth. So a few more interesting examples after we've done the basics. So in the text speak, strike, redress, in the find all, we want to find alphanumeric characters, and then we can go back up and have a look at what the curly brackets mean. And we find that the curly brackets are a repetition operator, meaning find me exactly so many copies of the regular expression. So in this expression, we're looking for exactly 5 alphanumeric characters, and we find them. And only one of them happens to be a full word. The other 2 are only whatever was found that has 5 characters. In the next example, we want to find something similar, but any a sequence of 9, of exactly 9 alphanumeric characters that only matches the word dangerous in our text. So something a bit more sort of efficient is to define sets of characters, which we do with angle brackets, like this. And characters can be listed individually, or if they're a sequence, they can be listed by using a hyphen. So everything from A to D, rather than listing the letters individually. And the usual special characters that we've already seen are not active inside sets declared with square brackets. And there are a few examples here for you to see. So let's test this. So we have a bit of a longer text here, and we want to find a specific group of characters. So we want a T, both a capital and a non-capital T, and then an H and an E that appear 0 or 1 times. So when we get the result, we have the full word the, both capitalized and not capitalized, and the single occurrences of the characters that we have declared inside. Defining groups is also very useful. Groups are declared with parentheses as opposed to the angled brackets for sets. And groups match regular expressions inside the parentheses and indicate the start and end of a group. They're very useful, particularly with working with URLs, and this is the example I've chosen here. So in our S variable, we have some URL, and in the search pattern, we use parentheses to look for separate things that we might want to be doing with the URL. So we want, let's say, to separate the HTTP. Then we want to look at, to see what the domain is, and then what the pages after the various slashes are. So looking at the tree, the hierarchy of this page. And then we print group 1, 2, and 3 to see what it looks like. So we have separated the HTTP, then we have separated the domain, the main bit of the website that we've chosen, and the third group is going towards the last page that we visited in this URL. Could be quite handy. So, moving on from groups, what happens if we actually want to match parentheses? Yes, so in this example, we used parentheses as a special character to look for groups. In the second example, we want to actually find only the text that is enclosed in parentheses. So we want to look for parentheses as punctuation, not as special characters. How do we do that? As we said, to escape a special character in a search pattern, we use the backslash. So backslash parentheses means find me an actual parentheses. Don't use the parentheses as declaring a group. And we do the same with the closing parentheses here. And inside the parentheses, we want to find any number of any characters. So we execute, and we do indeed find only the text from this few lines, which includes parentheses. And this, for example, since this is the text of a play, this could be stage directions or something. If you wanted to only extract the stage directions and you know that they're enclosed in parentheses, that would be a handy thing to do. So let's find bits of text. Let's create an expression to find all capitalized words in a text. We have again a few lines, and the expression that we would use is, in this case, we use square brackets to say find everything capitalized. So you'll see that the A to Z range is capitalized because that's what we want to see. Followed by any alphanumerical character. And we find indeed only the capitalized words. That will come up in a minute when Francesco starts. A slightly more complicated expression. So let's find the bits of text where characters are asking questions. Their speech ends with a question. So in the variable Octavius, we have a bit of dialogue, and the characters, we can see their names as well before the speeches they give. And in the search pattern, we are now going to use groups as well, because in one group, we want to see the name of the character, followed by the colon, as it is here in the text. And in the second group, we want to see the speech of that character. So again, inside the first group, we're looking for a range of capitalized words followed by any character. Then we know to expect the colon. And then in the second group, we have any number of characters followed by a question mark. As you'll see here again, since I'm looking for an actual punctuation question mark rather than a special character question mark, I'm escaping it with a backslash. And this is followed by a new line. We execute, and the result is only 2 lines. Both belong to Cassius, and he's asking questions both times. The rest is not questions, so it doesn't match. That's the use of both ranges and groups. As you see, it can be extremely handy. So the next, moving on from regular expressions and back to Python, very quickly going through 2 very useful types for storing data, and then I'll move on to Francesco. So there's a lot of text in here that I won't be going into now, but you can download the notebook and read it all, execute all the code, and play around and test it. So just very briefly now, lists in Python, we declare again with the name as variable. So the name of my list is Star Wars, and lists are declared with square brackets. The items in those lists are separated by commas. And again, if you're not sure what's the type of your variable, you can use the type function on it, execute, and you see that the type is a list. Dictionaries store information in a different way. So dictionaries again have a name, but this time they're declared with curly brackets. And they're collections of key and value pairs. So the key is followed by a colon and is followed by its value. And the same thing, you can perform a type function on the dictionary to see that that's actually a dictionary, to double check. Items in a list, you can access via their index. So 1, 2, 3, etc. to get the content. And it's the most important thing to remember is that indexing starts from 0. So if I want to find the first item in my Star Wars list, I want to look for the index 0, not the index 1. Then when I print, I get to New Hope. I go back to check. Yes, the first item is a New Hope. And this is how I get the last item. With dictionaries, it's slightly different. You can access the value using the key. So we said they go into pairs, keys and values. So if I execute this code, I'm looking for the content, so the value of episode 5, and the value of episode 5 is this, rather than looking through an index. So there is a lot of things you can do with lists. You can append items to them. I'll leave all of this for you to run and see how they work and play with them in your own time. You can insert elements at a predefinite index, so appending appends the new content at the very end of the list. If you want to insert something at a certain index, you use the insert function, not the append function. You can also, from dictionaries, for example, you can remove key and value pairs by using the key. As we said, everything you do in a dictionary, you do by using the key. And again, if you run this, you will see that the place London has disappeared from the new list, etc. Again, very briefly about input and output. So what people mostly do with, well, programmers, mostly do with Python is read and write data into files. And to do this in Python, we can open a file, read the content from a file, manipulate it, write it into a new file, or append the content into the old file. So all of this is possible. And there are 3 ways to open a file, 3 modes. With the read mode, you can only look at the content, extract it, use it, but you can't export it, can't write it. In a write mode, you can write content, but it overwrites the old content. So if you don't want to overwrite, but add new information, you would need the append mode. And there's a bunch of examples of how to open files and how to read from them and how to write to them. And all of these are available from this link, the practice texts and files used in this teaching book. If you go there, you'll find all of these examples of files, and you'll be able, when you download them, to use them here with this code in the notebook. And a very similar thing is working with web pages. Follows a similar logic to working with local files. And again, there are 2 examples here at the very bottom of reading a web page, performing here some of the string functions we talked about, then performing some regular expressions on those first results, so a second level of string manipulation, and then printing a list of separate words. Okay, so I leave all of this for you to look at in more detail and in your own time. And now I'm moving to Francesco. Thank you.
Thank you very much, Simona, and thanks to everybody for listening. Let me just start my screen sharing. Now at this point, I think you should all see my Jupyter notebook. Is that correct?
Yep.
Perfect. So, well, okay, we can go on with the second half of this session. And what I want to do in this second half of this session is really to show how to use basically all the basic construction of Pythons that Simona presented to you, and some more, and something more, and apply that to a real-life scenario, to sort of doing something that's of interest for, already doing something of interest for people that are interested in textual studies and manipulating informations in text. And so what we want to apply, and what we will apply Python syntax to, is a task of what is generally called natural language processing. So the way in which we use computers to interact, very basically, to interact with natural language and information like texts or other sources of language manifestations, like written, I don't know, recorded interviews or speech, something like that. But we will, of course, limit ourselves to text. I was saying we will apply that Python syntax to a task of natural language processing, which is called named entity recognition. Perhaps you will not be able to follow along through all the code that I am writing, but that's not that bad. Perhaps everything will make sense after the full series of sessions about Python will be completed. But in any case, you can always go back to look at our notebook and see if things become clearer and clearer, and so on. So basically, I will use most of the syntactic structures of Python that Simona presented to you, and I will introduce some bonus, some more advanced feature to you that will hopefully guide you to the next session. First of all, though, let's start by saying in general what we are trying to do. So what is named entity recognition? As I said, named entity recognition is that part of natural language processing, that task in natural language processing that tries to define automatic, programmable, computational ways to recognize in some input, like some text, named entities. So the problem now becomes obviously to define what a named entity is. We can use, for example, the definition in a very beautiful manual of two specialists of natural language processing, Juravsky and Martin, and work with their definition of what a named entity is. Well, very simply, roughly speaking, anything that can be referred to with a proper name. So basically, we can just say that a named entity is, in a text, is something that is referred by its proper name. Three prototypical examples are persons, locations, and organization with their name. But we should start by noting a couple of things. And the most important one is the second, that often in concrete application, the notion of named entity is stretched a bit to include other words that you would not exactly define as the prototypical proper names, right? But they do refer to some entities that are of interest for you. Let's consider one example, also taken from Juravsky's and Martin's manual. So this piece of text taken from some economic news where some entities have been recognized and labeled. So this is a typical output of a named entity recognition. So if you take the raw text, or text without tags, right, citing high fuel prices, United Airlines said, etc., 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 and you want to tag, to apply these tags that you see in green here in this notebook, to named entities so that we classify them, we obtain something like that. Could be an output of a named entity recognition script. And we note, by just looking at this example, we note three important things that will tell us basically what we need to know about named entity recognition for this session. The first, of course, is that named entity recognition is not just about recognizing names, so not just saying, oh, well, United Airlines can be a name of something, but it's also about classifying them. So the typical named entity recognition scripts will take your input text and not only identify proper names, but try to say what type of category this proper name belongs to. So in this case, for example, United Airlines is labeled as an organization, or Tim Wagner in line 4 is labeled as a person. Second, that you can immediately notice, is that named entity recognition is a powerful tool. It can be a text with this named entity information extracted can be extremely helpful to summarize what the text is about. So to try to attempt something like an automatic summarization. If we know what persons are quoted, what organizations, and like in this case, the times and some other information, we can already see what's happening in this text by simply looking at those actors, let's say. Third thing that you can notice, as I was saying before, is that you see some tags that are peculiar, like time Friday. Well, okay, this might still be considered somehow a proper name of the day, Friday, but we are kind of in a gray area, right? But definitely, if I asked you what proper names in this text are, I don't think many of you would have pointed me to $6 in line 2. Still, obviously, if you are using named entity recognition to do exactly what I said before in point 2, so to try and summarize what's happening, and what's happening here is that airlines are raising the fares of some flights connecting locations, where you might be interested to know when this modification of fares happened, and the amount of money that the fare was modified by. So in this case, the people who wanted to apply named entity recognition to that decided that they were interested in many entities, not just those that prototypically go with proper names, like Denver, San Francisco, and so on, but also some other mentions that belong to a rather to a gray area like $6. So this is a typical prototypical example of named entity recognition. This is this type of problems of classifications and classification of entities that are not quite exactly your typical idea of proper names are very, very often met in this type of text. So why I love Python and why are we doing this in Python? Well, there are many possible answers, but if you ask my opinion, it's because Python is very intuitive with the syntax. You probably, if you are new to programming, you're probably not appreciating that enough. But I can assure you that the presentation that Simona gave you of the basic operations in Python might have taken a long, long time with other programming languages. Whereas in Python, everything it's very intuitive, at least according to me. This is obviously subjective. The other, I'm sorry, I am very sorry, just give me a second.
We have a Sunoikisis dad scenario here, almost as famous as the BBC dad.
Except we don't have the video.
Sadly, yeah.
I'm sorry. Yes, yeah, I am.
No
okay, so what I was saying. Okay, why are we doing this with Python? Well, okay, Python syntax is very intuitive and very and easier than other languages, but this is obviously a subjective thing. You might think that other languages are more intuitive to you, but as for sure, one thing that I can tell you is that Python is extremely powerful. You can do a lot of things with Python. Simple statements like the one that we saw before, simple math operations like the one that, or simple string manipulations like the ones that Simona used in her examples, or more advanced things. And within these more advanced things, natural language processing is one of them. Now, Python has fantastic libraries fantastic modules to do natural language processing, and they belong to a big library, let's call it like that, called Natural Language Toolkit, which is linked in my notebook. With the NLTK, which the way it's often abbreviated, the Natural Language Toolkit, you'd be able to use a lot of pre-programmed function and access a lot of resources to do a lot of advanced operation in natural language processing. We will see a couple of examples today. Another interesting thing is the fact that NLTK has a sort of a spin-off, let's say, a sort of a project that integrates the same philosophy and apply that to ancient languages or historical languages, which is called the CLTK, the Classical Language Toolkit, which includes support to many resources and many corpora that NLTK does not cover. So it has a focus. It's sort of, you can imagine that as a sort of an NLTK, but with more focused on ancient languages. Again, this is linked in my notebook. One thing that so the first thing to do now that we want to make use of some of the functionalities within this library is, sorry, just let me run my Jupyter notebook, because the output of this cell is a little bit blurry now. For some reasons, it doesn't like the way that it does a strange reshaping on the cells. Sometimes it happens in Jupyter, so you don't see the code. Now everything is better. So the first thing we need to do if we want to use modules within those two libraries is to import them, like Simona showed. But you have to remember a couple of things. And a couple of distinctions within Python that Simona didn't have the time to mention. So If you want to print something, well, you can just go ahead and use the print function. Why? Because print is a built-in function. Print function, type function, or other methods that's for string manipulation that Simona showed are already loaded as soon as you load Python itself. I am already available. Of course, if I want to use some of the code that Simona used to search using regular expression, with a string called blah blah, I will not be able to do it because I haven't imported the regular expression, the RE module. But the RE module is part of the standard library, as it is said. So you already have it, because as soon as you install Python, the RE module is installed together with you. So it only with even a fresh, brand new installation of Python, all you have to do if you want to use it, RE, is just import it. CLTK and NLTK are not part of the standard library, so you don't have it. So if you run import NLTK or CLTK or those lines of codes within your Python code with a fresh, brand new Python installation, you will have an error that no module like that is found. Why? Because if you want to install modules that are not, if you want to run modules that are not part of the standard library, you must, before everything else, you must install them. But if you go to the web pages of these two projects, you learn how to do it, and it's Python makes it very, very easy to install new modules. So right now, let's talk about, as I said before, sort of a real life, or getting closer to a real life scenarios. And we want to use Python to work with a Latin text. And let's say, as Simona used early example from Julius Caesar, from Caesar's, from the Shakespeare's Julius Caesar, to honor the fact that today is the Ides of March. Now let's work with some text by Caesar himself. Let's say that we want to recognize and somehow classify proper names in the first book of Caesar Bellum Gallicum. Okay, so the Gaul War. So the first thing we need to do, obviously, is to get hold and to make our Python interact with the digitized version of a text. We could very, very easily work with the methods that Simona showed. So we download a copy, we go online to our favorite digital libraries of Latin text, and we download a copy of the Bellum Gallicum and read it in Python by using the read method that Simona showed. We read it, and we manipulate it that way we want. But this is okay. But we can make something a little more sophisticated thanks to the functionality of the module that we imported here in this cell, CLTK. What's that? Well, okay, this functionality, these two libraries, NLTK and CLTK, provide some function to load full corpora, not just individual text, and work with full collection of stuff, which is very handy whenever you start working with not just with one book of Caesar, but with a whole collection of Latin, classical Latin, or texts by Caesar, or even, a big collection of million of words. Now I will probably skip because first of all, because I've already done it, and secondly, because I don't want to take too much time, the following cell. But basically what you can have here is that you can use the sum function defined in CNLTK, like corpus imported that we imported over here, to download corpora to your local machine and then start working with. So basically what this function would do is list the corpora that are available, and here import a corpus, so download a corpus. And in this case, we will work with the Latin library. Why the Latin library and not, for example, some of the others like Perseus book? Well, just because Latin library comes in TXT files, so in TXT format. And we have a very, very handy corpus reader that comes with that. So that a function that very easily could read all of these TXT files into a corpus and let us manipulate that. All the things with CLTK go into are stored in a variable named CLTK data, and you can access the root of CLTK data, like for example, like with this line of code that I've just executed here. So if I just run this, I make use of this function defined within these modules of CLTK. So a plain, and I invoke and I create, technically speaking, I created this object called a plain text corpus reader, and pass a path of the pointing to my installation of the Latin library here. And then this, what's this? You might probably recognize this. This is a regular expression, right? This is a regular expression matching all file names that have something like that in their file names. So this would match, as Simona said, all characters, basically, up to a point that are followed, yes, by an extension, by a dot txt. Well, more correctly, I will have to do that because this is a real dot, right? Dot txt. Why? Because this is exactly the syntax that a corpus reader requires. If you want to know that, well, you can always read the documentation online by looking the website of this documentation, or you can do like Simona did in the code before and just ask help for CLTK, corpus, Latin plain corpus reader. Or if you are in Jupyter, it's very handy. You can even go do like that. You come to in the parentheses of the function, and you click in the Mac that I am using, it's a Shift tab, but I think it's everywhere. It's a Shift tab, and it can give you the documentation. First of all, what is called a signature. So all the documents that are required here by this function, and here a description of what this, and some example even of what those arguments are and what this function does. Here we have also a definition of what the parameters of the function are, etc., etc. So here in this case, we run this and we get a corpus object. So again, by looking, you can use this type function, but that will not tell you very much. It will tell you what type of object this is. Okay, it's a plain text corpus reader. It's a plain text corpus reader as defined in NLTK. So if you want to read about that, you can just go to the NLTK documentation and read what a plain text corpus reader is. A corpus reader has a lot of interesting methods that you can do stuff with. So you can do stuff on a corpus object, and you can have a full list, again, if you're in Jupyter, by going there, writing a dot, and then have a list of things. File IDs, it's a very interesting one. As the documentation says, returns a list of file identifiers by for the file ID that make up this corpus. So if we run this, we have a list of files that make up this corpus. So these are all the texts that we downloaded with the Latin library. It's a very long list. How many? How do we know that? Simona already gave us the answer. This is just a list of files. So we can just manipulate that as a normal list and just run the len function, and we know that this is the number of files. So more than 2,000 files. How many words are there? Well, I can already tell you that by using this important method, words, you can already have access to every single word in a sense in this corpus. We won't run this because it will take probably something like 30 seconds to run altogether. But I've already done that, and you can see that it's 1 million, more than 1.5 million of things. So let's go back to the topic of named entity recognition on Latin. So again, let's make sure that we know what we want to do. We want to do named entity recognition, and we want to break it down to a series of operations that we can tell our computer to execute using Python code. So basically what we need to do is go step by step, one unit of our text per at the time, and decide three things, make three types of decision. Whether it's a name or not, what type of entity it is, it's a person, location, or it's not an entity at all, and decide whether it's a part of name. For example, if it's a new in New York City or stuff like that, it's not just a name, it's not a name new, but it's a part of a name, So it's a component that belongs to a name. So we are basically working piecemeals, right? We are working 1 unit per time in our text. And those units that are processed one at a time in NLP are called tokens. And they are the products. So tokens are what you have after you perform in a raw text a process that is called tokenization. Most of the times, like in this case that we are with what we are doing here, named entity recognition, they correspond to our own intuition of a word. So basically a token is a word, but it's not said. And do not confuse these two levels. Most of the time, yes, in a prototypical situation, tokens are like words, but there are cases, like if you're working with tree banks, and now you know, after all these sessions, you know everything about tree banks. You want to, for example, take a word like don't in English, that's written as single string separated by 2 white spaces, but you want to probably take it as 2 tokens, one for the auxiliary part and one for the negation part. So this is one example of a word that do not correspond to a token. Or, for example, in Senatus Populusque Romanus, the famous formula, you're probably not taking, even if it's not separated by white space, you were not probably taking Populusque as a single token, but you want to separate the lexical word from the conjunction that is written together in our way of writing Latin. So the first task, decide what type of entity we have to requires us to define a tag set. Like, for example, a 3-tag system, person, location, organization is one that is very often used, and we reserve the 4th tag, which is generally O, for not an entity, outside an entity, so not part of an entity. Or maybe, and it's the easier one, we can do a much easier binary classification. So a system that just says entity and takes everything in this giant group, not an entity. We will, for this moment, just stick with this easier binary classification. So I said tokenization. Question for you: how would you tokenize a string like that? Gallius dominis diviso in parte stress. Well, yes, easier answer. Oh, sorry. No. I did exactly what I didn't want to do. I'm sorry. I didn't realize that I was in the... well, okay, we can just wait for this to finish while I write the code for this for this task that I wanted to tell you. I didn't realize that I was still embedded with in this cell. Let's see. No, it's still working. So how do we tokenize this sentence? Well, the easiest thing to do is just go with the white spaces and then use the method that Simona showed us. So S split with a blank space. S is not defined, obviously, because I haven't run it. Yes, see, this is the easiest thing you can do. Thanks for us, as we have seen with this long list. And you probably have noticed that when I showed you the long and complicated docstring of the plain text corpus reader initialization, a plain text corpus reader has already built in a word tokenizer. So the object corpus, when you invoke the words method on the plain text corpus reader, it is already doing the tokenization for our purposes. Let's define a very simple thing in that we can call in NLP jargon a baseline. So a method that will just give us the easiest possible solution that we can only improve for doing named entity recognition. So our baseline method will go through every token in this text and will make use of one of probably the easiest feature that we can think of that will reveal if something is an entity or not. The fact that we generally, and in Latin and in the way we write Latin, yes, we do, that we use the capital letter to mark proper names. So if something is a token starts with a capital letter, we append the label entity to it. Otherwise, we append the label not an entity. Okay. we are almost ready to start coding. The first thing that we want to decide is then what we do with this annotation. What type of data are we going to create? Well, if you think about it, linguistic information generally comes in different hierarchical level. We've got the long text as a stream of and sequence of character, like the one that we just read from our text. And this text can be conceptualized as a series of tokens. We have already talked about tokenization, so a series of words, for example. And so we can just simply append to this list of tokens another sub-list that contains token and then a tag. Or we can create, we might want to create an intermediate subdivision for the test, an intermediate subdivision for the test, like the sentence. So we say the text, and we split the text in sentences, and we split the sentences in words, tokens more correctly, each of which has a text and a label. Okay, Simona didn't mention that because it's generally a little more advanced and lists are more than enough for you to start with. But there is another type of object that's often used in Python to store collections of data, like lists, that is very often used for annotation. It's the tuple. A tuple is pretty much like a list, but it's declared with normal brackets. So a tuple like P is defined something like that. Token label type P. It is a little bit like a list, but it has a very important difference. The most important difference is the tuples are not modifiable. So you cannot do something like that. Tuple append extra tag. If you try to do that, we have an error because tuples are not modifiable. Why use tuples and not list? Obviously, we can write this information as a straightforward list like that. And then in this case, we can, oops, yes. We can append it very regularly. Now, let me comment it out. Why use tuples and not simply lists? Tuples are a little more efficient, and maybe if you don't want other people to modify or other processes, better, to modify the annotation, but to store that in an immutable way, that's a plus, the fact that they are not modifiable. So how do we verify? So first, we have decided that we want to create a sequence like this one, right? Text with a list and a list of tuples. The tuples will be a token and the label, token and label, and so on. And the labels are possible values for the labels are entity, not an entity. How do we verify if a token starts with a capital letter or not? We could use a regular expression for that, like the ones that Simona showed us. But perhaps this is a little bit an overkill because we already have some string methods like the one that Simona showed for string manipulation that will do the trick for us without writing a regular expression. Regular expression might be extremely handy if you want to improve on this baseline. So whenever you want to start making some improvements on everything, then you can start thinking of regular expression. But we do have some string manipulation methods that check the case of the string. Simona showed you the way to manipulate, to modify strings, like, for example, taking a string that it's lowercase and make it uppercase. But there are the equivalent version that simply check whether a string is upper, lower, or titled case. And let's see them in action. I won't have the time to discuss these bonus questions, but as you see, they return a peculiar type of object that can either hold the value of false or true. They're called booleans. So basically, they check a string and they decide: is Gallia written like that with capital G lowercase? No. It's uppercase? No, because it's not all in uppercase. It's title case? Yes, this is true. So is title case is what we are looking for. For every word, we will simply check whether is title return true or if it returns false. We can right now do something that is called looping through those tokens. What is looping? Where looping is just defining writing some lines of code that perform the same instruction all over the iterations. And what are the iterations? Where the easiest way to write a for loop is just to write something like that, some pseudocode like that. For, this is a type of loop that Python supports, for items in collection, and do stuff with item. So basically, we'll not, if this collection holds 1 million items, we will not have to say do stuff with object number 1, number 2, number 3, number 4, number 5, up to 1 million. But we'll simply say to Python, repeat do stuff on each item for each item in a collection. So in that case, if we are using this with the words or the tokens, to be more precise, of the Bellum Gallicum, we will do something. We will check if it's titled for all the if the is titled, the if title function returns true for all the words within the text. Now we can simply start writing the code like this, but maybe we will want to check after we finish checking book 1 in Bellum Gallicum. We want to move to Bellum Gallicum 2, or then to Bellum Civile 1 or 2, or other works by Cicero instead of Caesar. So what we want in this case is to be able to reuse our code, and for that we can define very well a function. What is a function? A function is a snippet of code, is a piece of code that can be reused. So it's defined once, and then you can simply use it pretty much like you used print before. So you invoke them, passing some argument to that, and it will take this input and performs the stuff that you declared in the definition of this function and return the output that you want this to return. So in this case, we can write some function that takes some tokens, perform some iteration in this token, like here in line 13, and then return something to us. So in the end, we will just be using this function, passing some arguments to that, so tokens, and we will have back this which is defined in the return statement over here. And what is this? What is this stuff written in red? Well, technically speaking, this is just some sort of a comment, you can say, but a special type of comment, which is the docstring. So I am writing the documentation of my function myself. Basically, I could leave that out, but if I want that to be more usable for the others, I can also write the type of documentation that we saw for the corpus reader before. So basically, we can do something like that. So so that basically, as soon as we will start using this tag sentence baseline, look, we can just ask for the documentation, and what do we have? What we get? What I've written over here in red between these 3 double quotes. And this informs the people about what type of parameters this function expects and what type of object it returns. So I will leave that out. Okay, so right now we want to just work not with the 1 million of words of the Latin library, 1.5 million of words, but just with the content of this files. And we can always pass to all the methods in a corpus reader the exact file names that we want to limit ourselves. So we are storing in a variable, like Simona did, the words, so the tokenized words, not of all the corpus, but just of this file. And we can check this out. Yes, this is pretty much the content of the first book, plus some indexing before. So as we are not interested in the files before, we will create a new list that just holds the items from object index 77. Remember, index starts with, so you see that the first word of Caesar's text is Gallia, est omnis divisa, etc., index 78, right? I've already done this. So remember, the list starts with 0, so word 78 is indexed as 77. So we just want this. And then we can run the tag baseline on that. Let's see the results. Okay, it had recognized that those, it has given us what we want. The fact that these words written with capital letters are to be tagged entity in the rule that we defined. Is it a good rule? Well, here we have a period, and the first word after a period is obviously written with a capital in the way that modern editions of Latin texts go. And so this would be, in this case, it works perfectly because gallos are an entity. Okay, it's a proper name of a tribe, of a people. But what if it was another word like ab, if its sentences started by ab aquitanis, etc.? Well, we would have a false positive. Right now, how do we visualize only the tokens that were labeled as entities? And how do we extract this list, since we are interested in extracting entities? In this sentence. Well, so and how many entities we have over here? Well, I have written this piece of code that will probably look very esoteric to you. This makes use of a syntax that's probably to be the last item, the last part of this that I cover here. But we already covered a lot, I think. So this is basically what we are seeing here in line 2 of this cell that at this moment has the running number of 60, is a syntax of Python that is called list comprehensions. It's a way of constructing a list out of some iterable with only items that match some conditions. And in this case, it works only with this item. So it says that we have extracted 976 items over here. This syntax might look exoteric, as I said, but in fact, it's very, very intuitive. I don't know if you're all familiar with the system of, I think it's an European thing, right? Of the language classes that are labeled with the letters from A to, I think the last levels you can reach is C1 and 2, etc. With A1 being in every class, language class, like the easiest class level. List comprehension, if Python was a natural language, would be the first thing covered in A2 in an A2 Python class, right? So the first thing you learn after you've completed the very beginner's level, so the A1 class. But you can already start seeing what the logic of a list comprehension is. See, for example, over here, what we are doing is constructing a new list. So we are declaring a list pretty much like Simona showed you, brackets, square brackets. Declare that we want to keep only the T elements, and T elements would be indexed. Of the T elements, we are just interested in the first. Remember, it's a tuple. We are just interested in the first element, so the word. And then here we declare a simple loop, like for loop, T in the iterable. So every token, for every token in this list, just take the token, the first element of the token, if and only if T1, so the second element in the tuple, match this string entity. Be careful, always when you're making some comparison, always pay attention to the fact that this is a double equal and not a single equal. Because single equal means assigning a variable. If I write a single equal, I am assigning the value 1 to A. But if I want to see whether A is 1, the value of A is 1, then I have to make this. The difference, well, A is equal to 2. No, A. But what if I do this? Well, then right now A is 2, because this is an assignment. This is a check. You can, list comprehension is probably an advanced topic because you can really write Python code and do Python stuff without needing list comprehension. But it's a cool thing to do. So you can definitely implement the same thing that we did here, right? So creating a list that was holding only the values that had entity as the second part for each token in this list. You can very well write a simple Python statement using the basic syntax of Python. So you create an empty list, first of all. Then you loop on your original list. You storing all the values in each of each item in this iterable in a variable called t. Then you check whether the t1, so the second element in t, because t itself is composed of 2 elements, is equal to entity. And if it is, then append the first part to this list. We use 4 lines to do something that we could do in just 1 line, like that. And it's easier to write after you get used to that, and you can okay, so the last thing that I would say is that the second question, so how many unique entities, right? Because maybe Galli is repeated 100 times, who knows, is using sets. What is a set? A set is a special collection of data that just holds unique, that just counts unique values. So let's say we define a list like that. Oops, sorry. Banana, apple, lemon, apple. How many items do we have here in this list? Well, we can count them, but I expect that it would be 4, right? But apple is repeated. So how many unique elements we have? Well, we can see that by simply converting this list to a set. So count that, and in fact, the set has 3 values. So the set L is just made of apple, banana, and lemon. So a set will only contain unique value. And this is very handy, very practical to count unique values within lists. So if we transform entities, this nth variable, to a set, and then we measure its length, we have the count of unique values within this set. So in this case, we know that we have 369 unique strings within our extracted entities. So the rest of this notebook will try to use CLTK, so a built-in named entity recognizer tagger within the CLTK library to compare the results. I can just tell you that CLTK makes use of another approach. It simply checks a string to a dictionary, and if it's this word, it's within a dictionary of named entities that somebody compiled, so of proper names somebody compiled, it will just label it as an entity. You can learn how to use this from here, and you can have fun comparing these 2 lists, but I won't probably have the time to cover this topic with you in this class. So with that being said, I conclude my my presentation.
Thank you very much, Francesco. That was great, and thanks, Simona, as well. That's great. Did anyone want to ask any questions or make any comments about that in the first instance? One thing that I've always found interesting about this particular exercise when you start is that when you have some slightly more advanced attempts at doing NER, it actually takes a while before they're as good as the baseline that you showed, right? We did something similar to this last year where we ran a baseline and then we ran NLTK's parser, and then we ran CLTK's parser, which recognizes Latin better than NLTK does, and neither of them out of the box were as good as the baseline. So
yes,
it's. I mean, I don't know. I mean, at what point you start to get improvement?
Well, you know, I was in last year class, so I remember very much. The big problem with the NLTK method, which is very sophisticated, it makes use of a sophisticated machine learning algorithm to train a model that then tag. But this method, this tag, since there is no a readily available tagger for Latin model trained on Latin, we just give it to show how it works. With the model trained on English, so we were just simply expecting English to work with Latin, which is obviously absurd. So it was more like more of an exercise. But yes, you can design very complicated feature sets to extract. So basically, One part that I didn't mention in my presentation is the fact that you do named entity recognition by extracting a bunch of features for each of the words and also for the context of words, and try to map these features to a tag, to a possible tag. We just took the very first features that can come to our mind, whether something is written with capital letter or not. There are other features that might be useful, and especially if you want to implement better distinction, like if you want to start distinguishing between person and location, then you probably need something more than that, obviously. So this is one possible answer to your question. It becomes more useful whenever you try to implement a better, more complex classification than simply just looking at entity, not entity. So if you want to distinguish, to discriminate between, I don't know, very simple example in English, when JFK is the number of is the name of the president of the United States, and when it's New York airport, then you need sophisticated stuff. Definitely, you need some stuff to do this kind of things. But you're right that it might take a while before you arrive at the level of a very simple baseline like this one, especially for a simple binary classification.
Yeah. No, that's fun. Did anyone else want to add anything or ask anything? I know we're slightly over time, so we shouldn't discuss for too long. But if not, then I'll just end with a reminder that next week we have some more use of Python for extracting information from texts, and the example we'll use then is adding morphological information to the to Greek and Latin texts, which should be very interesting. And anybody who wants to know more about CLTK in particular, which I don't think is going to be discussed next week specifically, there will be a Sunoikisis session just on the use of CLTK, which will be taught by Patrick Burns from New York University on April the 19th in the summer semester. So if you're interested, do come along for that. But for today, thanks very much again to Simona and to Francesco, and we'll see you all next week. Cheers.